4 of chapter 9, and my apologies for starting with the limits. So we forgot about it on example 1 and 2. So a converging one, again, is when, as I go through my sequence, I get closer and closer to one value. And if I do, that value is called the limit. If I don't get closer and closer to one value, then it diverges. And we have no limit. So let's try this one. This is 1 over 1, then it goes 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, 1 over 9,999. Is that? It's approaching a number, isn't it? It's getting smaller and smaller and smaller and smaller and smaller and smaller. It is limiting to 0. I guess I should say converges. This one converges. And its limit is 0. It gets closer and closer to 0. So let's look at this one. 2 over 1, 3 over 2, 4. Well, notice here I'm just getting bigger. And here I'm getting bigger. This one starts at 2. This one starts at 1. So the next one would be 6, what? Fifths, then 7, 6, then 8, 7. So what is it getting closer to? 1. If you notice, this is 1 and 1/5, then 1 and 1/6, then 1 and 1/7, 1 and 1/8, 1 and 1/9, 1 and 1/999. This one converges, and it is going to converge to 1. 2, 4, 6, 8, 10. That's diverse. It's just getting bigger and bigger and bigger. We're not getting closer and closer to anything. So there's no limit to that one.
You could say that's a virtue in
No, it's not virtual and real. What pattern is here? -1, 1, -1, 1, -1 to the n power. If I raise it to the first, it's -1. If I raise it to the second, it's +1. The third, it's -1. Then it's
It doesn't diverge. It doesn't come.
Is it converging to one number? No. If it does not converge to one number, then we call it diverging, or it diverges, even though it's not getting bigger and bigger and bigger, which is kind of what we sometimes think about for diverging. It's just not getting closer to one number, then we call it diverging. Now, what's really happening is it's just alternating back and forth between two numbers, but it's not converging. Finding limits of sequences. So here they have given us a formula instead of a list of numbers, and they say, is it going to converge or diverge? Now, in the previous example, we were kind of just using our math understanding of numbers to figure out what's happening, getting closer to some value or not. Well, there's a way to do it that is really related to graphing and asymptotes, horizontal asymptotes. If this was a function, f of n, and you were asked to graph this function, rational functions have vertical and horizontal asymptotes. So what I'm concerned about is there a horizontal asymptote somewhere that I am getting closer and closer to? That's what converging is if I'm getting closer and closer to some value. So often we have something that looks like this. You know, there's an example of a rational function. Well, whatever this number is, this horizontal number is, this thing is converging to it. As I go to the right, I'm converging to it. As I go to the left, I'm converging to it. So we need to go back in memory. How do I find horizontal asymptotes? Or I should say, how do I find end behavior? Well, we compare the degrees. If the degrees are the same, I divide the lead coefficients. The lead coefficient is 3. The lead coefficient here is 1. What's 3 divided by 1? 3. This one converges to 3. And if you graphed it, you would have a horizontal asymptote at 3. There you go. That is converging on the right and on the left on 3. There'd be a horizontal asymptote at 3. So one thing is we can have the same degree on the top and bottom. We divide the lead coefficients. Another thing we can have is the numerator degree less than the denominator degree. And that is always 0. It's y equals 0 is the horizontal asymptote if the numerator degree is less. This one converges to 0. It goes to 0. And the third thing we can have happen is the numerator degree is larger than the denominator degree. it's going to be a diverging one. If they are larger, if it's larger by 1 degree, then it's going to be a linear asymptote. Notice that thing is just getting bigger and bigger and bigger. Even if it's getting closer to this line, it keeps going bigger. If it's 2 degrees bigger, then we have, do you remember this? I have a 2nd degree asymptote. We converge, it looks like a parabola, or etc. But if the numerator is greater than the denominator, it's going to be a diverging series. That one diverges. So we can use that graphing understanding to know what we converge or diverge. Now, we are going to study 2 specific sequences because there are formulas that go along with them. Arithmetic sequences where we have a common difference. A common difference is every number has the same difference between them. 1, 4, 7, 10, 13. What's my common difference? 3. Now, how do I get my common difference? Well, I can take any number and subtract the previous one. 4 minus 1, 7 minus 4, 10 minus 7. Common difference. That is an arithmetic sequence. The other one, geometric, we have a common ratio, common quotient, or common ratio. We'll use the word common ratio. We are multiplying by the same thing, or if I divide them, I get the same answer. That's where ratio comes from. So let's see, 2, 6, 18, 54, 108. No, that's not right. 162. What's happening on this one? I'm multiplying by 3 each time. I have a common ratio of 3. How can I do it? 6 divided by 2 is 3. 18 divided by 6 is 3. 54 divided by 18 is 3. So those are the 2 specific ones we have formulas for. Somewhere in your mind, you need to dredge up the arithmetic sequence formula that has a common difference in it. Here it is. There's the formula that will find any term in an arithmetic sequence. I just take the previous term and add, oh, that's a recursively. That's recursively. Where's my other formula? There it is. They've hidden it right there. I'm going to call that a sub 1. You need to know those 2 formulas. The recursive one is really easy. Because what does arithmetic mean? I'm just adding the same thing to the previous term. Previous term plus my difference. The explicit formula, the one that tells exactly what it is, a sub 1 plus n minus 1 times d. So know how to write these 2? Let's try them out. For each of the following arithmetic sequences, find a, the common difference. So let's look at it right here. Find the common difference. Well, I'm just going to take -2 and subtract the -6, which really means I'm adding a 6. So -2 plus 6 is 4. Common difference. Part B. Find the 10th term. Well, if I want the 10th term, I am going to use this equation right there. A sub 1, let me write it out. A sub n equals a sub 1 plus n minus 1 times d. So if I want the 10th term, I'm going to take the first term, -6, plus the number of term I'm on minus 1. Well, if it's the 10th term, then 10 minus 1 is 9, times the common difference, which is 4. 9 times 4 is 36, minus 6 is 30. There's our 10th term. C, a recursive rule. Well, the recursive rule, a sub n, we're going to be using this one right here, is just the previous term, a sub n minus 1, plus the common difference, 4. That's the recursive rule. D, find an explicit rule. Now, we used an explicit rule on B, but we're going to find the explicit rule that works specifically for this one. So if I want the explicit rule, I know any term should equal the first term, -6, plus n minus 1, because I want it to work for any of these terms, times my common difference 4. And we'll just multiply it out and simplify it, and that will be our rule. Negative 6, distribute my 4, plus 4n minus 4. So I'm going to write my nth term first. I'm going to say 4n, negative 6 minus 4 more, minus 10. If I wanted the 10th term like we did earlier, a sub 10, I could use this. 4 times 10 minus 10. What's 4 times 10? 40. Minus 10? 30. Check. Sure enough, our thing works, just like we got last time. So let's try this again, but they make it a little more interesting by throwing in some logarithms. So part A, I'm supposed to find a common difference. Well, to find a common difference, I'm going to take one term minus the one before. Well, what do we do when I subtract logarithms? We don't go to a calculator.
Divide.
I can put it together. It means division. The natural logarithm of 6 divided by 3. Well, what's 6 divided by 3? 2. Natural logarithm of 2. That's the common difference on this one. B, I am supposed to figure out what the 10th term is. So I'm going to use the same formula. I'm going to use a sub n equals a sub 1 plus n minus 1 times d. So if I want to get the 10th term, first term is natural log of 3, plus 9 times the common difference, which is natural log of 2. Now I'm going to have to use my logarithm rules. That 9 can become an exponent up there. Natural log of 3 plus the natural log of 2 to the 9th. When I'm adding logarithms and I condense it together, it's multiplication. Natural log of 3 times 2 to the 9th. Natural log of, what's 3 times 2 to the 9th? 1536. There's my 10th term. Natural log of 1536. If you told me the right numbers. C, they want a recursive rule. Yeah, we didn't go to a calculator on this. We just used the properties of logarithms. C, a recursive rule. Remember, a recursive rule says take the previous term, a sub n minus 1, and add the common difference. There's my answer. There's the recursive rule for this one. Now they want an explicit rule. Please watch so that when you have to do this. Well, the explicit rule, I'm going to be going back to the same thing I did on part B. To get any term, I use my first term, which was natural log of 3, I think.
Yeah.
3. Natural log of 3 plus n minus 1 times my common difference, which was the natural log of 2. I'm going to multiply it out and simplify it. A sub n equals natural log of 3, distribute here, plus n times the natural log of 2 minus the natural log of 2. Well, I'm going to take that n and make it an exponent on that 2. Natural log of 3 plus the natural log of 2 to the n minus natural log of 2. Now I'm going to condense this all together. When I'm adding, it means multiplication, right? 3 times 2 to the n, 3 times 2 to the n. And when I'm subtracting, it means division. Divided by 2.
Yeah, so you can just take 2.
Now I can still go with this. Yeah. That is like a 2 to the first right here. So we're not quite done simplifying. Natural log, when I divide, it means I subtract the exponents. N minus 1. 3 times 2 to the n minus 1. That's the answer to that one. So that made us use the properties of logarithms to get that answer. So that's an arithmetic set of problems. Now let's work on a geometric sequence that has common ratios. Here is the formula that's the explicit formula. It will tell you exactly the 17th term or whatever you need. A sub 1, first term, times the common ratio raised to the n minus 1 power. And then the recursive is just the previous 1 times the ratio. So those are the two things we will be working off of for down here. Okay, so we want to find A, the common ratio. So if I want to find a common ratio, I'm just going to take one term divided by the previous. 6 divided by 3 is 2. There's the common ratio. B, I want to find the 10th term. A sub 10 is going to equal, now I'm using this formula right here, it's going to equal the first term times r raised to the n minus 1 power. Now I'll fill in numbers. My 10th term, my first term is 3. My common ratio is 2, raised to the 9th power. We just did that a minute ago, didn't we? 1536, 1536. C, find the recursive rule. Okay, recursive rule means take the previous one, multiply it by the common ratio. Take the previous one and multiply it by the common ratio, which I probably would write as 2 times a to the n minus 1. Either way is okay. And then they want an explicit rule for this exact one. So I'm going to be using this one right up here to make an explicit rule. So it's the same thing as part B. To get any term, I take the first term times the common ratio raised to the n minus 1 power. So to get any term, I'm going to take the first term, 3, times my common ratio, which is 2, raised to the n minus 1 power. That's all I can do there. That will give me any term on this one. We'll try it again. Same things, but our numbers just look a little different. So if I want to get the common ratio, I take a number and divide it by the one before. What do we do when I divide with powers? I subtract the exponents. Now to get a ratio, remember I took a number, divided it by the one before. That's how I figure out what I'm multiplying by each time. So this would be 10 squared, -1 minus a -3, or 100. You can call it either way, I guess. Part B, they want us to figure out the 10th term. So, in order to get the 10th term, I need to take the first term times the common ratio to the n minus 1 power. So my first term is 10 to the -3rd. My common ratio is 100. I'm going to call it 10 squared. Raised to the 9th power, since it's the 10th term, right? So that's 10 to the -3rd times 10 to the 18th, which is 10 to the 15th. And we're not going to write out that number. 10 to the 15th. See, they want the recursive rule. Recursive rule is always the previous term times the common ratio. So for us, the previous term times the common ratio. What was that, 100? So if you want to, 100 a sub n minus 1. And then they want the explicit rule. So if I'm doing the explicit rule, it's this thing. A sub 1 times r to the n minus 1. So to get any term, I take the first term, 10 to the -3rd, times my common ratio. I'm going to call it 10 squared, raised to the n minus 1 power. I can simplify that because exponents raised to exponents. A sub n, 10 to the -3rd, times 10 to the, I need to multiply, 2n minus 1. 2n minus 2. Now I can even do some simplifying of that. This part right over here, 10 to the -3rd. This comes from 10 to the 2n times 10 to the -2. Because when I'm multiplying, I add those together, right? 2n plus a -2 is 2n minus 2. Oh, I did. So I now can combine some things, right? The -3 and the -2, I can put that together. This is 10 to the -5th times 10 to the 2n. Oh, well, let's call that 10 to the 2n minus 5 power. So we're just using our properties until we've got it as simplified as we can. All right. Constructing sequences. The second and the fifth term happen to be 3 and 24. Find an explicit and then a recursive formula for the sequence if it's, first of all, arithmetic. Arithmetic means I'm adding some things, right? So my second term was 3. My fifth term was 24. So if I want to go from the second term to the fifth term, I would start with 3, and I would add 3 common differences.
Okay.
Since in arithmetic, I'm just adding a common difference, well, to go from the second to the fifth, I'd have to add it 3 times. 3 plus 3d. So that's how I get my 24. 3 plus 3d is how I got my 24. So I can solve for what my common difference is. 3d equals 21. D equals 7. Once I have my common difference, well, I could figure out what my first term is, because I need my first term in some of my formulas. Well, what my second term is my first term plus the common difference, right? So my second term, 3, must equal my first term plus 7. What's my first term? -4. So let's write an explicit rule. An explicit rule is the a sub n equals a sub 1 plus n minus 1 times d. For an arithmetic one, that's my specific explicit rule. So to get any term, the first term, which we figured out was -4, plus n minus 1 times our difference, which we figured out was 7. So I can just simplify this. -4 plus 7n minus 7, or 7n minus 11. That would tell me any term. Now, recursive are always really easy. To get any term, I just take the previous term and add my common difference. There's the recursive rule. Now let's try it with a geometric one. Now it's the same idea that my second term is 3 and my fifth term is 24. But if it's geometric, it means I'm multiplying. So if I wanted to get that 24, I'd start with my first term and multiply by that common ratio 3 times. Ratio once would get me to the third term, twice would get me to the fourth term, 3 times would get me to the fifth term. So r times r times r is called r cubed. So if I solve that, then 8 equals r cubed, and r must be 2, the cube root of 8. My common ratio must be 2. I'm going to use the same idea to get back to my first term. My second term would be the first term times the common ratio. So if my second term is 3, it's my first term times 2. So what was my first term? 3 over 2 was my first term. If I multiply that times 2, what do I get? 3. So now let's work on getting our explicit rule. And our explicit rule, a sub 1 times r to the n minus 1. That's the formula for the geometric one. So I'll just fill it in. To get any term, I take my first term, 3 over 2, times the common ratio, what was it, 2? To the n minus 1 power. And if I want a recursive rule, it's always just the previous term times the common ratio. And I prefer it to be written 2 times a to the n minus 1. I don't know which way your book writes it.
For the cars, explicit.
Yes.
Can you do like 3 times 2 to the negative?
2 to the n, and then 2 to the negative first.
No, like 2 to the n minus 2 powers.
Let's take that 2. I could write it as 2 to the n times 2 to the negative first. That's true.
But
Now if I'm multiplying all these together, that's really 3 over 2 times 2 to the n times 1/2, right? 3 over 2 times 1 over 2 is 3/4 times 2 to the n. We don't do it, but yes. That's another equation that works. That's another equation that gives the same answer. It doesn't particularly simplify it in this case, I guess, is why we don't do it. But that's true. Let's go to your calculators. How can we get our calculators to make some of these things? It says produce on a graphing calculator a graph of the sequence a sub k in which the terms are k squared minus 1. Well, if I'm going to graph, I need some values to graph. I kind of did it all there, but go ahead and get your calculator out, because I didn't show you how to get those things. And we're going to make a table, then we're just going to graph that table, is what we're doing. Now, we're going to learn a way to put these numbers in, since we're just counting up by 1, without actually going 1, 2, 3, 4. We're going to learn a little notation that we're going to use. So go ahead and hit your stats and go to, you want to maximize that thing. Hit your stats and go to edit a list. And you might need to clear out some lists. There we go. Clear, enter. Clear, enter. All right. There is a sequence command where the first thing tells us the formula, the second thing tells what the variable is, and then the third things tell where I start using that formula, and this tells me where I stop using the formula. Now, it's not real efficient to generate the numbers 1 through 10 this way. It's actually easier to enter them, but later on it's going to be a little bit easier. So on list 1, I'm going to highlight to the title right down here, I need to find the sequence command. I'm going to go to the catalog because I can't remember where it is. Catalog, and I'm going to go to S, PQRS. There's a shorter way that we'll have to look for it. Oh, what too far. You see that little sequence with parentheses after it. Oh, don't tell me you said the wrong thing. You want the sequence with the parentheses after it. I'm going to have to go back to my list. Go up to the list of 1 title. All right. Hopefully it will hold it. It automatically, when you hit the catalog, goes to alpha lock. There it is. Okay, there we go. Sequence. Now, you can use K if you want. You can use any letter. I'll go ahead and use K since they did, and I'll have to hit alpha to do it. So alpha K, comma, right above your 7 is the comma. Now my formula, I'm not doing anything but just taking numbers at a time. And my variable is K, so I'm going to hit alpha K again, comma. I'm going to start with the number 1, comma. I'm going to stop with the number 10, and then close my parentheses, and it will generate 1, and then it goes to 2, then it goes to 3, all the way to 10. Boom, there they are all. Now let's go over to list 2, and this is really where it becomes more useful, because in list 2, I'm supposed to put the answers when I go list the 1 squared minus 1. And let me do it the shortcut way. On list 2, I'm just going to say take list 1, square it, and subtract 1, instead of generating a sequence. I'll do that a little bit later. So second 1 for list 1, take list 1, square it, and then subtract 1 from it. And now hit enter. Boom, there they all are. Now they said we're supposed to graph that. No problem. Stat plot. I'll turn on plot 1. And we'll make sure the type is a scatter plot. X's come from list 1, Y's come from list 2. I like how mine all set. I'm going to zoom. I'm going to do a stat zoom. Actually, before I do that, I'm going to hit Y equals and clear out any equations that I may have. Ooh, I did. Clear. Clear. All right, now I'm going to hit zoom stat. What's that? Choice 9. Boom, there they are. We graphed them. So I kind of did some of those things already and left them up for you. Now we're going to go directly with your calculator in sequence mode. Enter the sequence, k squared minus 1, in the y equals 1 list. But it's going to be u sub n. It's not going to be y sub 1 equals when I put it in sequence mode. We're going to start with 1, and we're going to stop with 10. U minimum means what is the smallest answer that we happen to get? Well, if I start with 1, 1 squared is 1, minus 1 is 0. We have to tell it 0 is our first answer. So sequence mode, where we change all our modes on the calculator, the mode button. And then instead of function mode, we have now covered all the modes. Sequence mode. Now when you hit y equals, it's u sub n. I'm going to go up and turn off my plot 1. So I'm going to highlight up there and hit enter to turn off that plot. All right, now my minimum value, my first answer is 0 if I manually do that. Now u sub n, what is the formula? N squared minus 1. But I don't find n, I just hit my variable button. And now it automatically does an n. N squared minus 1. So I'm going to hit zoom stat again, I guess. I'm going to hit zoom stat again. Hopefully that will do it. Yep, there they go. There are all your answers. It plotted it for us. It defaulted to dots on this one. Last time we drew it as boxes. So let's see some more of what we can do. Generating sequences with calculators. We're going to practice that sequence thing that we just did. So explicitly they have defined the formula. And what will be my answers when I start with 1, 2, 3? So let's go back to our calculator, which I have somewhere. Here it is. So here's the calculator. I am going to do a sequence, clear. I'm going to go back to that sequence. I'm going to hit math real quick and see if it's in there. Maybe it's under the number. It's somewhere. There's the sequence where we don't have to go hunting for it in the catalog. I don't know where it is. Stuck in catalog. Sequence. I'll have to look it up. Sequence. There we go. Now the first thing is your formula. You can use any letter. We'll go ahead and use K just because that's what they did. So 3 alpha K minus 5. Minus 5. There's my formula. Comma. The second thing, I need to tell what the variable is because you can actually have more than one letter. We only have one letter. The variable is K. Alpha K. Comma. I need to tell where I start. I'm starting at 1. 1. Comma. I need to tell where I'm going to end. Well, I can't do it infinitely. So let's do the first 10. 10. Close parentheses. Hit enter. There you go. Wow. Negative 2, 1, 4, 7, 10, 13, 16, 19.
How do we keep on going?
I can't see
Arrow to the right.
That doesn't work.
It doesn't work on yours?
it. No, it doesn't.
Oh.
Oh, wait. You will press enter and then do it.
Maybe press enter and then arrow to the right. I don't know.
Enter again and then do it.
All right. We'll look at that part later.
That works for me.
The book shows you another way where you use your storage and kind of write a little program. You can play with that if you want to. The sequence generates it. Recursively, Now, recursively, calculators are kind of set up to do recursive things already. -2, clear out your screen. Hit -2, and then just hit enter. By doing that, it's stored it in the answer memory of your calculator. And then we are supposed to be adding 3 each time. So say +3, and then hit enter, 1, and then just hit enter. Yeah, and there, it just keeps adding 3 to your answer, is what it does. So it works for a geometric one too. If you said times 7 and hit enter, and then it would just multiply by 7 as you keep going. There you go. So recursively, your calculator kind of is set up to do something like that. Now there is a sequence, very famous sequence, called the Fibonacci sequence. Now why it is famous is it seems to be occurring in nature. They talk about counting the petals on flowers, and the number of petals tends to be a number in the Fibonacci sequence. Or if you have pine cones, if you count a row going around and then the next one going around, it tends to be, now it's not guaranteed, but it tends to be a number in that sequence, the Fibonacci sequence. So the Fibonacci sequence can be defined several different ways. But one of the easiest ways to define it is this. They tell you what the first and the second term are. They're ones. The first term is 1. The second term is 1. And then every succeeding term is found by adding 2 previous plus 1 previous. So if I want my third term, well, 2 previous is 1 plus 1 previous is 1. Gives me a 2. 1, 1, 2. Now add 1 and 2. 3. Add 2 and 3. 5. Add 3 and 5. 8. Add 5 and 8. 13. Add. That's the Fibonacci sequence. And so when you count those things like the petals, then you might have 5, you might have 8, you might have 13, you might have 21. You might have, not a guarantee, but it's highly likely that that will happen. Now they show you, and I'm going to show you that little kind of programming way. So there is an earlier one, so let's see what this notation means so we can stick it in our calculator. They say take 0 and store it as your A value. 0, store, which is right above your on button, alpha A, colon, 1 is going to be stored as B, so we can do both of them at the same time. So I need to find my colon. Can you find it?
Oh, yeah, alpha.
Is it the decimal? Yeah, I can't really read it on this. Alpha decimal, colon, and then take 1 and store it alpha B as B. That just allows you to do 2 things at once. So we'll just hit enter, and that performs it. 0 is the A value, 1 is the B value. Then they say take A plus B and store it as the C value. Alpha A plus alpha B, store it alpha C, colon, we're going to do something at the same time.
Wait.
So colon, where did it go? Alpha colon. Take A and store it as the B value. Alpha A, store it alpha B, colon, alpha dot. Take C and make it the A value. Alpha C, store it as alpha A. There's the first number. Hit enter. There's the first number in the sequence. Hit enter again. There's the second number in the sequence. Hit enter again.
We got a Fibonacci sequence in our calculator now?
There's the Fibonacci sequence. No, you'd have to start all over again to start the Fibonacci sequence. You could write a little formula, a little program, and store it in your calculator, and you'd have the Fibonacci sequence in there. I think I'm done.
Let's go.
Yeah. I'm done. Your turn.
We have to do all the lessons.
Yes. I finished the lesson. Now it's your turn to finish the lesson.
Can you figure out? Oh, wait.